Hello, my name is Fumitaka Mafune from the Graduate School of Arts and Sciences. Today I'll be talking to you a bit about challenges toward GX based on basic nanochemistry. As mentioned earlier, my area of expertise is basic chemistry, and I conduct experiments while thinking about how I can contribute to GX from that standpoint. I would also like to note that realistic experiments can be messy and unglamorous, and I actually hope you'll come away today with an understanding of the unglamorous side of things. The content of today's lecture is as shown here. To start with, one important keyword in basic nanochemistry is something called a cluster. After I talk about that, I will discuss its potential applications to GX. First off, a cluster is a type of substance made of a few to a few dozen atoms or molecules grouped together. To give you a rough idea, they can be grouped into these categories. Starting from the left, you have atoms, then clusters, and as those get a bit larger, they become nanoparticles, and once those get even larger, you get what we call bulk. So in that sense, a cluster is a type of substance that is quite small, but is larger than a single atom. When you hear the word cluster, you might think of the clusters of infections that occurred during the COVID-19 pandemic. But originally, cluster actually referred to a bunch of grapes. Accordingly, you could perhaps just picture a bunch of grapes, with a handful of individual grapes clustered together. One way to think about clusters is as essentially a bulk substance miniaturized to the extreme, or shrunk down as small as it could possibly get. However, they're still small enough that you can actually count the number of atoms in them, from several to several dozen to several hundred. Of course, once you get to around 10,000, you won't be able to count them anymore, but clusters are usually much smaller than that, typically just a few dozen. These are examples of clusters. The main player in today's talk is an element called rhodium, which is written as RH. Three rhodium atoms grouped together, with the cluster carrying a single positive charge, is written as RH3+. This is RH3+ here. 4 rhodium atoms grouped together is RH4+, and 5 rhodium atoms grouped together is RH5+, and so on. At the bottom, you can see 2 RH6+ clusters of different structures. In most cases, RH6+ tends to take on the octahedral structure shown on the right. But depending on the properties, it can also take on other structures, like this one on the left, which is called a bicapped tetrahedron. In any case, one of the reasons we study these clusters is that, unlike bulk, they have different properties depending on the number of atoms in the cluster, or what we call the size of the cluster. For instance, whether there are 3 atoms, 4, or 5. So one angle of our research is to make big clusters smaller, and perhaps discover new properties that didn't exist before. Another is to create clusters of different sizes, and study whether certain sizes show very high reactivity or some other interesting behavior. That said, today I won't be focusing too much on the differences between sizes, and instead would just like to emphasize that we are working on a very small scale. Today, I'll be discussing rhodium, which is a type of metallic element. When clusters are made from a metallic element, they are called metal clusters. Metal clusters are closely tied to catalysis, since catalysts often involve various kinds of metals. The target for this particular study was to observe the interaction and reaction between metal clusters and small molecules. Next, I'd like to explain why we focused on clusters. When it comes to catalysts and chemical reactions, we want to understand how atoms behave as precisely as possible. When mass spectrometry is used with clusters, it allows us to see exactly what's going on the molecular level. How many atoms there are, what kinds, and what happens when they react. This level of detail is a major advantage. This figure is of a mass analysis device. While I won't go into the details of the diagram, the section on the right is what's called the mass spectrometer, which allows us to clearly separate and analyze each atom. I'll be discussing this in more detail today, but when RH6+ reacts with NO, or nitric oxide, it forms RH6NO+. You can also add another NO molecule to get RH6NO2+. Or, if you replace one rhodium atom with a tantalum atom, you get RH5Ta+. And reacting that with NO gives you RH5TaNO+. I think the greatest advantage of this method is that it allows us to distinguish and observe all of these individually. Another advantage, and this will come up again later, is quantum chemical calculations, which are run on computers. In cases like these, where there aren't many atoms involved, say 6 rhodium atoms, 1 nitrogen, and 1 oxygen, that number of atoms is small enough that we can determine structure and energy through quantum chemical calculations with a high level of accuracy. The second point is the potential for applying this research to GX. Since today's theme is GX, I'd like to briefly share our thoughts on this topic. One of our main goals is to visualize and understand reactions between catalysts and molecules at the atomic level. One particularly important reaction is the reduction of nitric oxide, NO, by rhodium. While there's a lot of talk about electric vehicles these days, if you actually look around, most cars on the road still run on engines. When gasoline is burned and reacts in an engine like that, it reacts with the nitrogen and oxygen in the air. At high temperatures, that combustion process always produces nitric oxide, NO. In cases of incomplete combustion, it can also produce CO, or hydrocarbons. What we want to do is convert these through oxidation reduction into nitrogen gas, CO2, and water. Substances that are not very harmful to us physically. Which may then be safely released or emitted into the atmosphere. To make that happen, we actually use what's called a three-way catalyst, which is made from platinum, rhodium, and palladium. This type of catalyst is widely used in many different systems. As an example of how it's used, 2 molecules of nitric oxide, NO, and 2 molecules of carbon monoxide, CO, can react to form N2 and CO2, which can then be released safely into the atmosphere. The most important thing here, and the critical first step in the reaction, is cleaving the bond between nitrogen and oxygen when the NO molecule adsorbs onto the surface of the rhodium, the catalyst. If the nitrogen and oxygen stay bonded as a molecule, the reaction won't proceed. So cleaving that NO bond is the most critical first step. To explain that, we often use a diagram like this one. On the horizontal axis, you'll see something called the reaction coordinate. Just think of it as the reaction progressing from left to right. On the vertical axis, it says relative energy. You can think of it as showing the energy of each substance. Lower always means more stable, and higher means less stable, so going downward visually means becoming more stable. When rhodium reacts with NO, the first thing that happens is that the NO molecule adsorbs to the surface, forming a structure like this. But if you want to ultimately cleave the NO bond, you need to separate the nitrogen and oxygen atoms, which means forming a structure like the one on the very right. However, if you look at the left and right sides here, you'll see that moving from left to right involves climbing this hill. This hill is what we call the transition state. It is thus very important to figure out how best to lower this hill. If the hill is low, the reaction proceeds smoothly. If it's high, the reaction won't happen easily. So what we're looking at in today's talk, and our topic of research is, what are the requirements for further promoting the dissociation of NO? Before we dive into the actual science, I'd like to touch on something else about rhodium. Namely, that it's a material whose price fluctuates wildly. If you look at this graph that I pulled from a certain website, the price of rhodium in 2018 was under 10,000 yen per gram. By 2021, however, it had skyrocketed to around 164,000 yen per gram. Since then, the price has gradually leveled off, and in recent years has been hovering around 25,000 yen per gram. So as you can see, it is a substance with major price swings. As for why it fluctuates so much, rhodium is what's called a platinum group metal, a type of rare metal, quite a precious element. It is mainly mined in places like South Africa, Russia, and North America, and is primarily used as catalysts. This means it is highly sensitive to things like political instability or economic activity. So from a research perspective, one of our goals is to find something that behaves like rhodium, but isn't actually rhodium. If we could make a rhodium-like material from something else, that would be huge. It's not easy, of course, but that's the kind of challenge we're looking at. And in the context of environmental science, like GX and so on. On the right here, you can see the global annual mean temperature anomalies. The bottom, or horizontal axis, shows the years, and the vertical axis shows the temperatures. As you can see, the global average temperature just keeps rising. And last year, as I'm sure you all know, it was particularly hot. So this is the context we're working in. And this is the data that science can clearly analyze and confirm. Meanwhile, we have President Trump, who famously said, "Drill, baby, drill," during his campaign. In other words, drill all over the place, drill as much oil as possible in order to stimulate the economy. And he was later elected. And then there's former UK Prime Minister Sunak, and the speech he gave in September 2023. Originally, the UK had declared it would end the sale of vehicles equipped with engines by 2030. In his 2023 speech, however, Prime Minister Sunak announced that the deadline would be extended to 2035. So considering all of this, our belief is that environmental issues like this are not purely issues of science or technology, but issues that are heavily swayed by things like politics or economics. I wanted to touch a bit on that broader context as well. Since today's audience is Spring GX, and I know you're not all necessarily from scientific fields, and come from a variety of backgrounds. Now, let's get into the main topic. Today I'd like to first talk about visualizing the catalytic reduction of NO. As I said before, the key point is whether the bond in the NO molecule, or nitric oxide molecule, is dissociated or not. The clearest way to determine this is actually an experiment. NO is a molecule, which means it vibrates. Here it says free NO equals 1876. This 1876 refers to the wave number when the NO molecule is just floating around, not attached to anything. Its vibration frequency shows up at a wave number of about 1876 centimeters to the power of -1. There is already this reference table that tells us what the wave numbers will be when the NO molecule adsorbs onto a solid surface. So the idea is, if we carefully track the vibration of NO on the surface of the rhodium, we can tell whether the adsorbed NO molecule is still intact, or whether it's dissociated. That's the logic behind this approach. If you look at this chart, for instance the column labeled N, you'll see numbers like 310 and 440. These are actually quite low in terms of photon energy. The low wave numbers mean that the photon energy is also low, meaning emitting sufficient light in this wave number range is actually quite difficult. That's why we travel overseas and use a free electron laser, specifically the one at Radboud University in the Netherlands, to run these experiments. These are our co-researchers, Bucker on the left and Olga on the right, who we have been conducting these experiments with. So how do we actually measure the spectrum? It's a very unusual process. For those of you in the sciences, when you think of measuring an infrared spectrum, for instance, you probably imagine just popping a sample into a nearby device, hitting a switch, and getting your data. But when it comes to cluster research like this, we have to use a very unusual method to measure the infrared spectrum. It's a method you've probably never heard of, called the infrared multiphoton photodissociation method and messenger method. Let me briefly explain. We start with a rhodium cluster with one NO molecule adsorbed. That we can prepare. Next, we weakly adsorbed an argon atom to the sample, just weakly sticking it on as the first step. Then we shine infrared light on it. What happens is, and those of you in the sciences might recall learning this in your first year at university, you begin getting vibrational levels, like this. When we shine the light, it gets absorbed, like this, and results in a higher vibrational level. But if you just leave it alone, what happens is something called thermal relaxation. This means that the energy gets spread out across the whole cluster. As a result, the argon atom, which was only weakly adsorbed, gets desorbed and slips away. We then detect the moment when the argon slips away, and generate the spectrum from that in a sort of indirect two-step method for measuring the spectrum. More specifically, before we shine the infrared light, we measure the intensity of two types of clusters, those with NO adsorbed to the rhodium, and those with NO and argon adsorbed. Then, after shining light on them, we look at how these intensities change. Because of the mechanism I just explained, the intensity for the ones with argon decrease when hit with light, while the intensity for the ones without argon increase. By comparing how much one decreases and the other increases, we can ultimately generate something like this, what's called a spectrum. The horizontal axis here shows wave number, which corresponds to energy. This could also be wavelengths. The vertical axis shows intensity, specifically the intensity of the infrared response. Each of these spikes, or peaks that you see, correspond to and allow us to measure what's called the vibrational spectrum. Now, what I'm going to show you next is this. How does the spectrum change when we add one NO molecule to rhodium, or two, or three? And what can we learn from these changes? Let me explain that briefly. Apologies, this explanation might be a bit messy or unglamorous, but I'd like to take the time to walk you through it. So at the very top, here is the actual spectrum we obtained. Below that, labeled B, C, D, and E, are the stable structures of RH6NO+, which we calculate using something called quantum chemical calculations. We also ran vibration calculations for each of these stable structures, and those are shown in the chart as well. Looking at this, you can see that the one on the top is the most stable, the second from the top is the second most stable, the third from the top is the third most stable, and so on. You'll notice these numbers here, like 0 electron volts, 0.004 electron volts, and 0.27 electron volts. These are energy levels, and the higher the energy, the more unstable it becomes, with these listed in increasing order. According to our calculations, the most stable structure is the one where the NO bond is ruptured and results in two separate atoms. The second most stable structure, however, is one where NO remains intact as a molecule. Now let's cross-check, so to speak. Let's compare our actual experimental results with the results of our calculations, to see what was actually produced. Cross-check in that sense. First, as you can see from the results of the calculations, there are actually multiple possible structures, or what we call isomers. In this case, we labeled them 61A, 61B, 61C, and 61D. And because they are all reasonably stable, it wouldn't be surprising if all of these were produced to some extent. So in terms of cross-checking, what I want to focus on first is this spot right here. There's a very strong peak here. Now when we look for what might match this peak, it would probably be this. There's a peak here between the 1500 and 2000 centimeters to the power of -1. As for what it proves, it is a clear indication of molecular adsorption. In fact, that is the only thing it could mean. When there's a molecule adsorbed, it produces this strong peak here, meaning, when we compare this and this, we can determine that this is likely the isomer that was formed. So that part's all well and good, but then you might look at the left side and wonder what's going on there. And it turns out that it's probably not just the 61B that was formed. Why? Because if you try to cross-check using just 61b, the number of peaks doesn't quite line up, and it feels a bit off. So then we look closer, and we can predict that 61a and 61d are also in the mix. Now, I'll admit that there's definitely some ambiguity, but the takeaway from these results is that, while 61b was the main isomer that was produced, 61a and 61d isomers were also generated at the same time as well. In other words, we're seeing a mixture of isomers appearing together. One more analysis we can do with the results we obtained is see what percentage of the nitric oxide molecules have had their bonds dissociated. From this, it looks like roughly 3 to 5% have had their bonds dissociated. The next topic is what happens when two molecules are adsorbed. I'll be skipping some parts, as I'll be conducting the same analysis. Just like before, we can measure the spectrum of a cluster with two molecules. We'll look at how the spectrum changes compared to the single molecule cluster, and how it matches up with our calculations. At the top is the spectrum we actually obtained, and below that are the structures that we obtained through calculations, and their corresponding vibrational spectra. There are, as expected, multiple possible structures that could have formed here. So let's cross-check and see what we can conclude. What I'd especially like to focus on is this peak that has appeared on the far right. If you take a closer look, you'll notice it appears to have a jagged top that is split into two, perhaps even three peaks. In fact, we believe there are actually two or even three peaks here. With the reason being that, when there are two NO molecules adsorbed to a cluster, they each vibrate independently and show up at slightly different positions. That's why this peak here is split into two. And if we analyze this area below that, it seems that, with these two peaks here, there has probably been this 62b produced, and also a bit of this 62a mixed in to some degree, and so on. That's how we approach it. And finally, the analysis for when there are three molecules is exactly the same, so I'll just skip over this part here. But ultimately, we believe that we can assign, this process is called assignment, the structure of 63A to this cluster. Now, our real aim all throughout this process was to get the diagram you see at the bottom right. Basically, what we really wanted to do was illustrate, in a sort of schematic, what happens when 1, 2, or 3 NO molecules are adsorbed to the rhodium hexamer. As I said at the very start, our goal was to precisely control the number of atoms or molecules involved in a reaction, and visualize what happens in each case, when there is 1 molecule adsorbed, 2 molecules adsorbed, and so on. This has allowed us to visualize the reaction in this manner. In this diagram, the thickness of the arrows represents how dominant that reaction is, meaning the thinner ones can still occur, though they are less likely. At first, it mainly binds in molecular form, as does the second one. But with the third one, it looks like there are 2 molecules adsorbed, and another adsorbed in dissociated form. So this kind of diagram gives us a sense of how the reaction might actually proceed. We can draw similar diagrams of what happens with clusters of other sizes. I'll skip over the details here as well, but for instance, we've just looked at RH6+, but what happens if it were RH7+, or RH8+? When we fix the precise number of atoms and molecules involved, we can visualize what kind of reaction will occur and how it will occur, and visualize it by drawing these kinds of diagrams. Creating diagrams like this is one of our goals. That said, there's really no such thing as a perfect experiment. It's very common for some aspect to get simplified, or for an experiment to not fully match real-world conditions. In this case, one very important factor is the effect of temperature. For these experiments, we cool the clusters themselves first to around 200 Kelvin, or minus 70 degrees Celsius. Meanwhile, in the actual catalytic converters used in automobiles, which clean up exhaust gases, the reactions occur in blazing hot temperatures of around 800 Kelvin, or about 500 to 600 degrees Celsius, as they handle exhaust gases that have just come out of the engine. So there's a bit of a discrepancy there in that sense, and we can't fully account for it in our experiments. Still, I think it does a solid job of allowing us to understand the fundamental properties of rhodium and NO as substances. At this point, you might be thinking, sure, rhodium is used in all of this, but it doesn't seem all that incredible. We're working so hard to use rhodium to cleave this bond between the N and the O, but it doesn't actually seem all that effective. So what we did, to see whether there was a material that could cleave that bond perfectly, was to conduct an experiment where we replaced one rhodium atom with a tantalum atom. This here is the spectrum for a cluster with 5 rhodium atoms and 1 tantalum atom, and an NO molecule adsorbed. Apologies for it being in the opposite order as the previous examples, but A is the experimental result, while B and C are the results of calculations. What we found in running our calculations was that when tantalum was introduced, B became by far the most stable. Compared to B, C ends up with much higher energy, meaning high instability. Basically, once you introduce tantalum, it's pretty much only this super stable structure that ends up forming. And when we cross-check the spectrum from that perspective, it's crystal clear what the match is. Comparing A and B, you'll notice that there are no peaks at all in the 1500 to 1600 centimeters to the power of -1 range, meaning all NO bonds have been dissociated. That's why there are no NO vibrations. Then, around 950, there's a very sharp, prominent peak sticking straight up. That's from the oxygen atom adsorbed to the tantalum, with the O vibrating like this on the tantalum. So things like that, and also this other strong peak around 500, shown here in red, that corresponds to a nitrogen atom sitting in the middle of 3 rhodium atoms, vibrating as if it were moving in and out, like this. All of this aligns perfectly. If you look closely, the match is ridiculously good. In that sense, this is probably the best match between experimental and calculated values I've ever personally achieved. But what I really wanted to emphasize, and what I think you now understand, is this. That just replacing a single rhodium atom with tantalum can change the reaction so dramatically. So then, how did replacing just one rhodium atom with just one tantalum make the cluster that much more reactive? How did just a single substitution change the reaction this much? This diagram shows the result of the calculations we did to investigate this. We compared clusters with the same number of atoms, the pure rhodium clusters shown in red, and RH5TaNO+, or clusters where just one of the 6 rhodium atoms has been replaced with a tantalum atom. The diagram on the left shows the results, obtained through calculations, of how things change. What I want to draw your attention to, as I mentioned at the start of the lecture, is that the reaction progresses from left to right, with the vertical axis representing energy. Higher means less stable, and lower means more stable. Now if you look at the black line, including the dashed black lines, starting from the initial point all the way to the final state, you'll see that it's not exactly a downhill slope, but that there aren't any hills or barriers, meaning the reaction can proceed quite smoothly. Now look at the red lines, the pure rhodium clusters. This is the same one I showed you earlier, but you can see that, when starting from the initial point, there is still this hill remaining here. So what this tells us is that the drastic change in reactivity when tantalum is introduced is due to that hill being lowered, or the products becoming much more stable. So why does adding something like tantalum make the cluster this much more reactive? Let's think about that for a moment. To explore this, we conducted a series of experiments using various combinations. We looked at combinations of pure rhodium and iridium, where all 6 atoms were comprised of the same element, as well as the combinations 5 rhodium and 1 tantalum, and 5 rhodium and 1 iridium. We examined these to see how the reactivity would change, and discovered some notable trends. To examine why the properties of RH6+, IR6+, and RH5Ta+ differ, we conducted this kind of comparison. We compared how energy levels would change when a single nitrogen atom or a single oxygen atom was adsorbed to RH6+, IR6+, and RH5Ta+, respectively. When you add one nitrogen atom to RH6+, you get this kind of substance. And when you add one nitrogen atom to IR6+, you get this kind of substance. And when you add one nitrogen atom to RH5Ta+, you get the substance shown on the left. However, the energy difference before and after adsorption is almost negligible. In other words, adsorbing nitrogen to these particular substances doesn't significantly change their energy levels. On the other hand, we found that when oxygen is adsorbed to RH6+, IR6+, or RH5TA+, the level of energy stabilization caused by the oxygen is completely different. This is the final conclusion. In terms of what it can tell us, it allows us to make this sort of diagram. When we plot on the vertical axis the percentage of dissociation, when NO is adsorbed to rhodium, we see that for RH6+, it was at most about 5%, and that it was 100% for RH5TA+. Meanwhile, for iridium, T was around these values in the case of RH5IR+. Now, if we plot the bond cleavage with oxygen, as calculated earlier, on the horizontal axis, and compare the two sets of data, we find a very strong correlation. In other words, at least in the case of rhodium, the conclusion we can draw with regards to how to cleave NO bonds is that an element can dissociate NO if it has strong affinity for oxygen. This means that the ease with which the NO bond can be broken is strongly correlated with the bond energy between the element and oxygen. This is the conclusion, and now a quick summary. In summary, in this experiment, we focused on the NO reduction reaction, using what we call hexamer clusters. Hexamer clusters are what we call clusters comprised of 6 atoms. We wanted to see the NO adsorption states of these hexamer clusters. To do this, we controlled the number and types of atoms in each cluster, and the number of NO molecules adsorbed. Then observed what happens under those specific conditions. The method we used for this is called the multiphoton photodissociation method. The result was our first achievement, in which we created a sort of schematic that illustrates how the NO adsorption state changes. Meanwhile, we also looked into what factors ultimately make NO easier to dissociate, which is something that can be used in the design of catalysts. The conclusion we came to was that there is a strong correlation between an element's affinity with oxygen atoms, in other words, how strongly the element binds with oxygen, and NO dissociation behavior. But that doesn't mean the discussion ends here. Well, why not just use a bunch of elements with a high affinity for oxygen then? Unfortunately, it's not that straightforward. This is because if the affinity for oxygen is much too strong, it can cause problems further down the reaction pathway. For instance, as I mentioned earlier, carbon monoxide, CO, might need to react with oxygen to form CO2. But if the oxygen atoms that were originally formed in this way and left behind remain too tightly bound to the catalyst, they can actually block or hinder subsequent reactions. So it isn't as simple as it seems. That said, at the very least, I believe this approach and these design principles may offer valuable insights in terms of cleaving the NO bond. But thinking along these lines, you might wonder, what's the point of cleaving these NO bonds? Aren't most cars going to be electric in the future anyway? There might not even be cars that release exhaust gases. So what's the future in something like an NO reduction catalyst? Some of you who are young might be thinking this. But there's actually another miracle we have to consider here. Rhodium, as it turns out, also likes hydrogen. And in the future, how we'll transport hydrogen will become an important issue. Here, in terms of how we can adsorb hydrogen, transport it, and release it where needed, rhodium again shows significant promise. This is why I find rhodium to be such an interesting element. Here are some data from past experiments. In this case, hydrogen was blown onto the surface of solid rhodium, and measurements were taken to determine how much of it would adsorb or stick. Results showed that a large amount of rhodium adsorbs to the surface of the solid. As for what we mean by large amount, we use what is known as coverage rate, which tells us how much of the available adsorption sites are actually occupied. In this case, the coverage was 1.8, meaning the sites were almost all occupied. However, this hydrogen does not dissolve into the solid, it only adsorbs on the surface. So then you might think, why not use rhodium in the form of nanoparticles? Nanoparticles are tiny, just about 1 nanometer, so the ratio of surface area to volume is high. The idea was that, since hydrogen adsorbs onto the surface of rhodium, if we prepared rhodium as tiny nanoparticles, we would get lots of hydrogen adsorbed to the surface. This is by a group from Kyoto University. On this chart, the horizontal axis represents hydrogen pressure, and the vertical axis represents hydrogen over rhodium. This is the ratio of adsorbed hydrogen to rhodium atoms. So, the higher the value on the vertical axis, the more hydrogen has been adsorbed. Looking at this data, we can see that the amount adsorbed increases as the size of the nanoparticles decreases. This is entirely reasonable. The smaller the particle, the greater the surface area relative to its volume. As the surface area to volume ratio increases, H over RH, or the number of hydrogen atoms relative to rhodium atoms, comes to be about 0.23. This is actually a pretty remarkable finding. Naturally, our next thought would be, well, why not make them even smaller? That brings us to the rightmost part of the chart. What happens when we move from rhodium nanoparticles to clusters? This here is data from an earlier study. If we look at these, we can see the data on the horizontal axis is reversed. It represents the number of rhodium atoms. 50 means a cluster made of 50 rhodium atoms, 10 means a cluster made of 10 rhodium atoms, and so on. The question is how much hydrogen adsorbs to these, or the D per RH, with D being deuterium. This refers to heavy hydrogen, but for our purposes, you can think of it as the same as hydrogen, H. What we see as the cluster size decreases is that the D over RH ratio increases. In simple terms, the smaller the cluster, the more hydrogen binds per atom. Looking at it this way, if H over RH is 8, in other words, if H per RH is 8, then for RH2+, there would be a total of 16 hydrogen adsorbed to the 2 rhodium atoms. That's a huge number of adsorbed hydrogen atoms. As for what structure it has, it would look like this. When there are 16 hydrogen atoms adsorbed to 2 rhodium atoms, it looks like quite a large amount, almost like the hydrogen is coating the rhodium. As for how they're adsorbed, you'll see these 2 bridge hydrogens, written as 2H. Bridges are hydrogen atoms positioned between the 2 rhodium atoms as if to bridge them. Then there are 2 terminal hydrogens, which stick out like spikes from the atom. The rest are actually adsorbed in molecular form, laterally as molecules. This part is a bit tricky, but the bridge and terminal hydrogens exhibit ionic bonding properties between RH and H. In other words, the hydrogen atoms carry a slight negative charge, and the rhodium atoms a slightly positive charge. This makes the compound resemble a metal hydride, or show similar properties. On the other hand, when the hydrogen bonds in molecular form, it's known as a sigma complex. You can see that it creates this structure known as a sigma complex. We thought this was interesting, and looked into how the hydrogen atoms would behave with other elements. Here, we've compared it with results for chromium, manganese, cobalt, copper, silver, and gold. But for instance, for copper, silver, and gold, you only get about 7 to 8 hydrogen adsorbed, or 10 at most. Again, rhodium has a comparatively high number. Meanwhile, looking at this top part, cobalt also has a pretty high number, 14, which is fairly substantial. Interestingly, cobalt, rhodium, and iridium all fall into the same vertical column on the periodic table. This suggests that metals in this area tend to adsorb hydrogen more readily. So with that, I'll skip ahead a bit here. What we've seen is that rhodium can bind with a large number of hydrogen atoms. Figuring out how best we can utilize this property is what we're aiming for next, or what we're currently working on at this moment. However, when looking at this from the perspective of hydrogen storage, there are of course certain requirements that must be met. If we really start thinking about practical applications, we run into some major obstacles, like what's written here. The 6.5% at the start here refers to weight percentage. meaning the hydrogen to metal weight ratio needs to be at least 6.5% when looking at it overall. This is actually a pretty tough requirement, because rhodium is an extremely heavy element. Say hydrogen is adsorbed to it, like in the earlier example, with 16 hydrogen atoms on 2 rhodium atoms. The rhodium part would weigh about 200, and the hydrogen part about 16, making the weight percentage about 8%. 8% for RH2H16+. But as the size of the rhodium cluster increases, this number will go down. So in reality, using rhodium for hydrogen storage may not be so viable. And there's another obstacle. Even if you did use rhodium to store hydrogen and transport it elsewhere to use, you would need to heat it up, and this would need to happen at a temperature between 60 to 120 degrees Celsius. You could say the hydrogen releases at 300 degrees Celsius, but that's no good. It doesn't meet the requirement. So in that sense, the bar is quite high for hydrogen storage. Now, due to time constraints, I'll skip over some of this, but the story actually continues, with us studying whether rhodium would release hydrogen when heated. I'll skip over the details as we don't have time. Let me just share the results of these various experiments. Here it is. This part here is what's important. Look at the horizontal axis, and only at the bottom chart. The horizontal axis represents temperature. The blue shows when hydrogen is released in the case of an element called vanadium. The red shows at what temperature range hydrogen is released for a cluster known as CO5+. And the black shows the temperature at which hydrogen is released for rhodium hexamers. What we see here is that for vanadium and cobalt, we have to raise the temperature to around 800 or 600 degrees Celsius before the hydrogen desorbs. Otherwise, it stays stuck and won't release. However, rhodium in that sense is a very remarkable element, as all of its hydrogen actually desorbs at around 400 Kelvin, or 100 degrees Celsius. We summarize the results in this chart. To jump straight to the conclusion, what we found was that rhodium clusters, compared to other elements, both adsorbs more hydrogen atoms and has a remarkably low desorption temperature. The rhodium hexamer we discussed earlier is especially impressive. It desorbs hydrogen at very low temperatures, meaning it releases rapidly with only a slight increase in heat. This is a highly unusual property. Today we explored sub-nanoscale clusters, or clusters, and in particular, how using mass spectrometry to examine them allows us to precisely define their atomic composition, and gain an accurate understanding of the behavior of atoms within them. We're now thinking about how to take the guidelines and expertise we've gained through this research and apply them to manufacturing. In a sense, we've already gotten the information, so what we're now aiming to do is figuring out how to reflect that in the creation of new things. That's the direction we're moving in our research. With that, I'll conclude this lecture, with acknowledgments to follow.